And so as we looked at, here are some things here. Again, we're going to see more word problems as we do stuff today in this part. When you integrate a rate, you get net change. Integrate a rate, you get net change. So the integration of rate of change is net change. So the integration of velocity we learned earlier was what? Wasn't it our displacement? It was our change in position, basically. Change in position. Hey, what Greek letter or geometric figure can we use for change in? Yeah, we can use delta. Okay, we can use delta to represent that. So, as we apply here, now be careful. Like number 2, we just got to set up the equation. We don't have to solve, but we just got to set it up, and we see some of those from time to time. So number 1, it says a storm has washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate there, I'm going to underline it. Keep that in mind. The rate at which the distance between the road and the edge of the water was decreasing. Decreasing. During the storm, and is modeled by that equation, R of t equals e to the negative sine t, feet per hour, t after the storm began. The edge of the water was 200 feet from the road when the storm began. There's my initial start, 200 feet at the beginning. If the storm lasted for 4 hours, how far is the water from the road after the storm? Sweet. We started at 200 at the beginning of the storm. Now, here's where we got to be careful. The distance between the road and the edge of the water is decreasing. So should I be putting a minus sign or a plus sign next? Because right now, before the storm started, it was 200 feet between the two things. But as the storm progresses, the distance between the two are decreasing. So that means I need to put a minus sign between the 200 and my integral. And so my integral will be from 0 to 4 hours of r of t dt. Again, I'm going to go in there and plug that in, let it do all the work for me. So I'm going to go in, get my calculator, and then in y1, we're going to put in e, so second ln, and then we're going to raise it to the negative sine t, negative sine x. That looks good. Get out of there, and then go math number 9. And then we're going 0 to 4 of y1. I got an answer. However, I have to subtract that from the 200. So 200 minus that answer. Oop, that's a negative sign. Minus. There we go. And I get that equal to be 196.937. That's what we get. And we got units, right? Feet. Always want to make sure we put the units. We'll lose a point guaranteed on a free response if we don't put the units there. Automatically a 8 out of 9. All right. Next one. A store is having a 5-hour sale. The rate at which shoppers enter the store after the sale has begun is modeled by the function E of t, okay, which is measured as shoppers per hour. So again, it's still a rate. When the sale starts, there are already 70 shoppers in the store. So that's the beginning, starting with 70. Write down, but do not solve. Write the equation involving an integral to find x time when the number of shoppers in the store is 200. Okay, so this is great. This is like a perfect multiple choice question on the AP exam. And it could be on a subpart of a free response. If they gave us what E of t was as an equation, then we could actually solve for what time it was to be that. But right now all we can do is we started off with 70. Come on, pen. We started off, come on, pen. Here we go. 70 plus, they were entering the store from 0 to 4 hours, E of t dt. And I want to figure out when does that equal 200. And then I'm done. Again, all they wanted me to do was write an equation to figure it out. We don't know what, we don't know what the E of t equation is, so we can't go any further to solve for the time. Did it happen at the 3rd hour? Did it happen somewhere between the 2nd and 3rd hour? We don't know that. Yes, sir. Yeah, my bad. I don't know where I picked 4 out of. I'm sorry. The last one had 4. That's why. It was just still on my brain.
How many hours?
Yeah, you should use a variable, yeah. I'm sorry. That was really, I wish I could back up and redo that part, but I can't. Yeah, we should be using X's. We should be using those, but in the grand scheme of things, we're okay. Oh, you're right. That's where I should stop. Yeah. All right, let's get back here. So we got our 70 plus an integral from 0 to some time. We don't know what that time is when that equation, when our thing is of dt. No, we'll leave it there. We will leave it like that now. And then when does that equal 200? All right, there. So yeah, the 5 goes away. The next needs to be where the 5 is. Okay. We know sometime between 0 and 5 hours. We just don't know when it's going to be. Is it going to be equal to that? Equal to 200. Now we do know that, hey, we're assuming no one leaves the store. Common sense is they are going to be coming and going, but to make the things a little bit easier to do, that's what we're going for. Jeffrey.
I would think of the integral, like for the bottom one instead of 0, it would be x is greater than 0, and the top one would be x is less than 5, because after the 5 hours, the rate of change would change.
We don't have to go that far into the thinking. Yeah. Too much thinking. Too far into the problem having fun is what that is. All right. Keep it simple. All right. All right. Number 3. Look at part B. Left Fremont sum. Oh, it's coming back and getting us. All right. So water is pumped into a tank at a rate modeled by R of t. I will try not to make a mistake here as I remind you about these. Those were some of our weak points, was doing tables with the Riemann sums. We did have some of those troubles a little bit when we were doing stuff, when we did that in the earlier chapters. Water is pumped into a tank at a rate modeled by the function R of t, liters per hour, where R is differential and decreasing on 0 to 8 and stuff. There are selected values of R of t as shown in the table below. At time t equals 0, there was 500 liters of water in the tank, and so forth. They ask us, what does the integral from 0 to 8 of R of t dt represent? So this is not a solving. This is just, hey, explain what it means in a sentence. So this is the amount. Again, R of t was a rate. So that the integral of R of t is the amount of water pumped into the tank over the first 8 hours. Okay, so that's the amount of water pumped into the tank over the first 8 hours. All right. Part B, estimate what the amount of water is that was being pumped into the tank over those first 8 hours using a left Riemann sum. All right, so with that in mind. Again, we're doing rectangles, not trapezoids, so that's even better. Our first one, the x value would be 1 times, so our width is 1 times, we got to use the left value, 3,000. Plus, our next rectangle is from 1 to 2, so that is 2 times the left 2,500. Plus, then we go from 3 to 6 for our next rectangle for a width. So that would be 3 times 2,100. Plus, the last rectangle is 2 times the left one, 1,500. Again, this is not one where we take 8 minus 0 and divide it by something because they don't tell us how many rectangles to do. Okay, so this one we have to, go do 4 rectangles here is what we're doing. Starting with the left one. What does that work out to be? 17,300 and it's liters. So over the 8-hour period, 17,300 liters was pumped into that tank. Now, based on the estimate, how many liters are in the tank after 8 hours? Well, that one's just saying it started with 5,000, and I got to add what I just pumped into it. And so 22,300 liters is what's in that tank after the 8 hours. Okay, so that one's just saying, hey, let's basically do the 5,000 plus the integral of what we just did. That's what that one's basically asking us to do. It's actually getting us to add that initial 5,000 to it. Now, do you have to show that one? No, but you do need to show some math. You just, on a free response like that one, you just can't throw down 22,300. You got to give it some reasoning on how you got that number on a free response. Okay, I know you can do 17,000 plus 5,000 in your head, but you got to show some form or fashion. Either take the previous answer and add the 5,000 to it, or you show the script of how you got that, how you're going to get that number. Okay, but you just can't throw down 22,300. All right, last one. Same scenario of the tank, but this time the table values of W of T is the number of liters of water in the tank at a given time. So not being pumped in, so it's not a rate, it's being pumped in. Or that was, it's just what it is there right now at each of those timing intervals. So a little note here, notice that is not a rate. Not a rate. So they ask us, what does this represent? The integral from 0 to 8 of W prime of T. Well, technically, if we think back to the previous problem, R of T is basically W prime. So we can actually use the same type of script here. It's the amount of water that is pumped into the pool I want to say pool. I'm just thinking of pool. I don't know what. Sorry, tank. Over 8-hour period. All right, now they ask us to find the integral from 0 to 8 of W prime of T dt. Okay. So, notation-wise, what is the integral of W prime of T dt? Isn't that just W of T? Isn't what that is? The integration of W prime, isn't that just W of T? So I just need to take W of T and evaluate it from 0 to 8. So I need to figure out what is W of 8 minus W of 0. Well, W of 8, according to this table, is 22,000. Minus W of 0 is 5,000. Which gives us 17,000 liters. Now, our answers are a little bit different, but they're pretty much close. And the reason why is, again, is because they were just a little bit more in the rate it was filling at the time and so forth. And so then they probably also picked nicer numbers to work with to do this part. And stuff is what they probably mainly did. So, since we weren't given the true equation.